You ever really look at your phone charger? I mean, it's just a little white block, right? But what's happening inside is kind of like magic. It takes the wild, chaotic electricity from your wall and, well, it tames it, turning it into the smooth, steady power your phone needs to survive. And the tiny hero behind all this? A little thing called a diode. So let's break down how it all works.
All right, so here's the game plan. We're going to start with the absolute basics, the different types of materials. Then we'll see how we can kind of supercharge them to do our bidding. From there, we'll build our PN junction, which is the heart of the diode. We'll see how it works as a one-way street for electricity and then put it to work converting AC to DC. And finally, we'll check out some other cool diodes you probably use every day.
Okay, so to really get how a diode works, we gotta start with what it's made of. And when you're talking about electricity, pretty much every material on Earth falls into one of three main camps.
First up, you've got conductors. We all know these. Think of a copper wire. These are basically the superhighways for electricity. They're jam-packed with these free electrons that are just itching to move, ready to carry a current whenever you ask them to. Then, on the complete other end of the spectrum, we've got insulators, like the rubber coating on that copper wire. These are total roadblocks. Their electrons are locked down tight. They're not going anywhere, which means electricity just can't get through. Simple as that.
And then, right in the middle, that's where things get really interesting. We have semiconductors. Think silicon. Now, these materials, they're not great at conducting electricity, but they're not complete insulators either. They're kind of like the quiet country roads of the electrical world. And believe it or not, that in-between property is their superpower.
Okay, look at this table. The first two rows, conductivity and resistivity, they make sense, right? High, medium, low. But that last row, energy band gap, that's the secret sauce. Think of it like a cover charge at a club. For conductors, there's no cover. Electrons can just walk right in and start the party. For insulators, the cover charge is like $1 million. No one's getting in. But for semiconductors, the cover charge is small. It's manageable. And that's the key. That's the part we can actually mess with.
So we've got this material that's just kinda okay at conducting electricity. How do we turn that into the bedrock of literally all modern electronics? Well, we do a little bit of what you might call atomic level engineering. We hack it, and this process has a name. It's called doping.
Doping really is the secret sauce here. I know the name sounds a little sketchy, but it's an incredibly precise process. We're talking about mixing in just the right amount of impurities, tiny amounts of other elements, into a perfectly pure silicon crystal. It's how we customize the material to give it the exact electrical behavior we're looking for. And by doing this, we can create two different flavors of silicon. That's pretty cool. If we add impurities that give us a bunch of extra electrons, we call that N-type for negative. Simple enough. But if we add impurities that create an absence of an electron, what we call a hole, we get P-type for positive. Now, a hole isn't really a thing. It's just a space an electron could be. The bubble and water analogy is perfect. The bubble moves up, but really it's the water moving down to fill it. Same idea here. This hole acts just like a positive charge, moving through the material.
All right, so now we have our two custom materials. We have our N-type, loaded with extra electrons, and our P-type, full of these electron-hungry holes. On their own, they're kind of neat, but when you join them together, well, that's when the magic happens. This moment, this simple junction, is what changed the world. The second these two materials touch, physics just takes over. All those free electrons on the N side see those inviting empty holes on the P side, and whoosh, they rush right across to fill them up. This happens in a tiny little zone right at the border, creating a thin layer that now has no free charges left. No extra electrons, no holes. We call it the depletion layer. And this layer, it instantly acts like a barrier, a wall, that stops any more electrons from making the jump.
And just like that, we've made something brand new. That barrier, that PN junction we just created, that is a diode. But you have to understand it's so much more. This simple concept is the foundation for almost everything electronic. We're talking transistors, processors, computer chips. It all starts right here. And its first, most basic job, to act like a one-way street for electricity. So here's the really clever part. We can control that barrier. If we apply a voltage in the right direction, what we call forward bias, it basically gives the electrons a push, shrinking the barrier and letting the current flow right through. Boom, the switch is on. But if we flip the voltage the other way, reverse bias, it pulls the charges apart, making the barrier even bigger.
It slams the gate shut. The switch is off. It's a valve, an electrical valve. Okay, so a one-way street for electricity. A valve. Why is that such a game changer? Well, let's go all the way back to your phone charger because that's where this all comes together.
So here's the fundamental problem. The power coming out of your wall socket is alternating current, or AC. It's chaotic. It's flipping back and forth, 60 times every single second. But your phone, and pretty much all your electronics, they need direct current, or DC. That's a nice, calm, steady flow in just one direction. They're completely incompatible.
So how do you fix this? You need a translator. In electronics, we call this a rectifier. And the absolute star of the rectifier circuit is our humble diode. It acts like a traffic cop at a crazy intersection, only letting the current flow in one direction. It takes that chaotic back and forth AC and forces it into an orderly one-way street.
Now, there are a few ways to build one of these. You can do a simple one with just one diode, but you end up throwing away half the power. Not very efficient. But with a clever setup using 4 diodes called a bridge rectifier, you can capture the whole thing. And check out that ripple factor on the chart. That's just a fancy term for how bumpy the DC power is. You can see the bridge rectifier gives us a much smoother output, which is exactly what we want.
But even with the best rectifier, the output isn't perfectly smooth yet. We get what's called pulsating DC. The traffic is all going the same way, but it's still kind of choppy, stop and go. To get that perfectly flat line of power your phone wants, we add another part, usually a capacitor, to smooth out all those bumps. Okay, so that basic diode we've been talking about is an absolute workhorse. It's everywhere. But that's just the tip of the iceberg. By playing around with the doping and using different materials, engineers have come up with a whole zoo of specialized diodes that do some really amazing things. Take the Zener diode, for example. This thing is designed to work backwards, something that would destroy a normal diode. It just sits there, blocking all current in reverse, until the voltage hits a very specific, preset level. Then, bam, it lets the current flow. Think of it like a super precise safety valve, and it's used all over the place to make sure voltages stay perfectly stable.
And then there's one you definitely know, the LED, the light-emitting diode. It's just a diode. It's a PN junction, but it's made with special materials so that when those electrons jump across that barrier, they release their energy not as heat, but as light, as photons. The indicator light on your laptop, the screen on your phone, the headlights on a new car, that is all just diodes, millions and millions of them, all working together, turning electricity straight into light. How cool is that?
It's just incredible when you step back and think about it. We take one of the most common elements on Earth, silicon, tweak it in 2 slightly different ways, and then just stick them together. And from that one simple junction, we get everything. Phone chargers, LEDs, the processors and supercomputers. It all comes back to this. So, the next time you plug in your phone, maybe you'll see it a little differently. It's not just a plastic block. It's a tiny, brilliant piece of physics with millions of little one-way streets inside all doing their job perfectly. And it really makes you wonder, doesn't it? What other little bits of magic are hiding in plain sight all around us, quietly powering our world?